All right, we're going to talk about rotational kinetic energy. Now, just like linear kinetic energy, when an object moves, it takes a certain amount of energy. When an object rotates, it takes a certain amount of energy. So let's draw ourselves a ball, and let's talk about a piece of mass somewhere out here on the edge. So if I turn it into a kind of a wheel and say, well, let's look at this piece of mass right here. Well, it's going to have linear speed, right? If I have it roll, the ball's rolling, this direction, this piece of mass is going to have a linear speed downward here, right? And it's going to go around and move around this way. So I have to account for the energy it takes to move it. So let's look at linear kinetic energy. So linear kinetic energy is going to have a form that looks like 1/2 mv squared, right? We've done this before. We've been doing this for months. So it's going to have to look something like this because it's just going to be the rotational analog of this. So let's draw another layer on this shape. Perfectly circular. Wonderful. There we go. And say this piece of mass, what's it doing? Is it going to have the same linear speed? Can I use the same formula? No, because it's closer in. So when the ball rolls, every piece of it is going to have the same angular speed, but not the same linear speed, right? Because the stuff on the edge is going to be moving faster because, well, V equals omega r, right? So the stuff out here on the edge will travel faster because it's going to have the same omega, but a bigger r. Okay, so V's out. I can't use V. So what can I use instead? Well, we said omega is going to be the same for every point on the wheel because it's a solid. It's all connected. So I can't have the inside bit or spinning faster than the outside bit or spinning slower. It's got to go at the same speed, right? Okay, so with that in mind, I need to use omega. So I'm using angular stuff, which makes sense because rotational kinetic energy. I should be using angular speed or rotational speed. So let's write this down. So I want rotational, let's call it ROT, equals, let's just bring that 1/2 in there because it's going to have the same form. And I'm going to use angular speed. But what goes right here? I left a gap here. Well, that's going to be mass, but can I just use mass? No, because it has to be the rotational equivalent of mass. Now, when we talked in the torque section before, we said that the rotational equivalent of mass was moment of inertia, and that's going to be I, right? Moment of inertia. So I for inertia is and that's going to act like angular mass or rotational mass. So let's put that guy here. All right, that looks pretty similar, right? So I've got 1/2 mv squared. I've got 1/2 I omega squared, and that's going to be rotational kinetic energy. So now, what do I put? Like, is it the same thing? It should have. See, I don't know. Does it look the same? It's pretty similar, but it should still be joules, right? It should still be joules. So should have units of joules. So we can check that, right? And we make sure it's still the same thing. So Joules, joules. All right. Let's go ahead and slide this up. So my formula is 1/2 I omega squared. So I know we said before that the basic formula for moment of inertia is going to be some constant times mr squared. Now this constant that would be in front would depend on the shape. But for us, we're just going to, we're talking about just like a point mass here or a bunch. And I mean, it's going to be important. Like it's going to factor in. But just for checking the units, I guess we can say it's just going to be mr squared. So I guess I should say times some constant, right? Okay. So now if I take that and I plug that into my I omega squared formula, I can go a little farther. But I also want to take in that we know that omega is equal to V over R, right? So if I just have I guess what we're doing is we're doing a point mass rotating around. So I now have rotational kinetic energy. So it is 1/2 I omega squared. But if I replace this I with mr squared. I'm going to put it in parentheses so you can see what I'm replacing. And I replace this omega with v over r squared in parentheses, so that goes together. So I'm going to get, let's pull these guys out of parentheses. So it's going to be 1/2 mr squared times v squared over r squared, right? So this and that cancel. So I am actually left with 1/2 mv squared. So for a single particle traveling around a circle, its rotational kinetic energy is actually just equal to its linear kinetic energy. So, and this is the same form, so we know it's going to have units of joules, right? Okay, so let's go ahead and talk more about this. So let's say I have a wheel, like a cylinder or something, rolling down a hill. And I want to figure out what its speed is at the bottom, right? Can I just consider rotational kinetic energy? So let's draw our picture, because you should always draw a picture. So hill, wheel, we'll say, velocity is this way. So that means it's going to be rotating. Its angular speed is this way. Now, I personally just like to draw the picture just so I get a good feel for what's going on, as you guys know. Okay, so this is what's going on. And so it's going to be translating and rotating, right? So it's got a translational kinetic energy or linear kinetic energy. It's got a rotational kinetic energy because its center of mass is moving. So we have to include both. So my kinetic energy is going to be my linear kinetic energy plus my rotational kinetic energy, right? So this will look like 1/2 mv squared plus 1/2 I omega squared. So now if I say it's going to roll down a hill of height, let's say, let's just call this 2 meters here from top to bottom. So how would I do this? Well, I'm going to do this just like I would in regular stuff, except this is my kinetic energy term now. So I would say my potential energy is going to be big at first. At first, my initial potential energy is going to be mgh, right? And my final potential energy needs to be 0 because we're saying it's at the bottom. So I want to convert all of my potential energy to kinetic. So, and my kinetic energy, since we're releasing this from rest at the top, my initial kinetic energy is 0, and my final kinetic energy is that term up above. Let's write that again. Plus 1/2 I omega squared. Oh, I never wrote this is equal to 0. There, got it. Okay. So now, I'm just going to do this like I have all of the energy problems we've been doing all year long. So now I'm going to say my initial kinetic energy is equal to my final energy. So my initial energy equals my final energy, but my only term that matters for initial is mgh, and my only term that matters for final is my final kinetic energy. So I'm going to have, let's slide up a bit. That looks good. mgh equals 1/2 mv squared plus 1/2 I omega squared, right? So here's where it gets like, what do I do? How do I find speed? I don't know my omega, I don't know my v, and I don't know I. Well, we can look up I, or it'll be given to you. So like this is an AP problem, right? So AP Physics 1. So you're either going to be told I or asked to find it. So in this case, I'm going to tell you your moment of inertia. So for a cylinder, your moment of inertia is going to be 1/2 mr squared. So let's go ahead and put your 1/2 mr squared in for I, and let's go ahead and, since we know omega is going to be v over r. Oh, I wrote that off the side of the page. There we go. So let's go ahead and replace both of those. So now I'm going to get mgh is equal to 1/2 mv squared plus 1/2 times your moment of inertia, which is 1/2 mr squared, times v over r. But all of that is going to be squared. Okay, so looking at this, something I should notice, of course, is this r is squared here, and that's squared here, so I can cancel this r with that r. And let's go ahead and say, oh, look at that. I've got mass here, and mass here. All those are gone. Because just like when you drop an object, rolling objects, the mass shouldn't matter. The mass is going to cancel out. Okay, so I have GH equals 1/2 v squared plus 1/4 v squared. So let's simplify that a little bit and say I now have GH equals 3/4 v squared. And we're solving for v, so let's kick the 3/4 to the other side, make it 4/3. We'll take the square root. So then v is equal to the square root of 4/3 GH, right? And at this point, we're in calculator territory. You just put your numbers in, and we'll say 4/3 times 10 meters per second squared times 2 meters, and you take the square root of that. So let's get my calculator out, because I don't do square roots in my head, and neither should you, because it is probably going to be easier and faster when you're actually doing the AP exam. So let's put this over here. It's good visible there. So you'll notice that on this mode, your calculator on an iPhone, you turn it sideways to get square roots and things. So if I want to do that, I want to do 4/3 times 10 times 2, and I'm going to take the square root of that. So my final speed, should be 5.16 meters per second. Not bad. Now, something I'd like to point out here is if we had just said, okay, let's drop a ball from 2 meters, right? What would how fast would it have gone? Well, we can just do in our head mgh equals 1/2 mv squared. So you're going to get let's slide this over here. Sorry about that. Trying to conserve paper a little bit. So dropping ball. So we're going to say mgh equals 1/2 mv squared. Cancel the m's. Multiply the 2 over here. 2gh equals v squared. So v equals the square root of 2gh for drop. Let's call this drop. We get something very similar. Now, let's compare the two. So I've got v drop and v roll. All right. So they're always going to look the same. It's got to have the same units. It's always going to depend on g. It's always going to depend on h. The only difference is what this constant out front is going to be. And this constant is going to depend on shape. And it depend on the shape alone. Ooh. I'm writing 2 different papers. All right. There we go. That constant depends on the shape alone. So if I had a ball instead of a cylinder, or if I had a hollow wheel like a hula hoop or something, it would have a different number there. And so it's only going to depend on the shape relative to other things. So the mass won't matter, the length of it doesn't matter, Just like, is it a cylinder? Is it a ball? Is it hollow? Is it not hollow? Something like things like that. The other thing we should notice is that it's always going to be slower to roll it than it would be to drop it, right? That makes sense because, dropping should be faster. But what if I said, all right, instead of rolling it, or instead of dropping it, I'm going to have a box on a frictionless plane. How would you find the speed of that? Well, what you'd actually do is, since there's nothing to lose energy to, is you're going to say mgh equals 1/2 mv squared, and then you're going to solve for v. And so a box on a frictionless plane, you're going to get v equals root 2gh. So this is going to be faster than this, right? But this makes a lot of sense when you think about it. It should be faster because with a ball rolling, you have friction. It's going to be slowing it down. So I'm going to lose energy to the friction. But another thing I have to consider is when I go back over here and I say that mgh, your potential energy, isn't just going to your speed. It has to get shared between your speed and your rotation, right? So it's got to go between more things. It's really tempting to look at this and say, oh, there's more terms on the kinetic energy side, it should be faster. But the truth is, because there's more terms, this value over here, which is your constant, which determines how much energy you have, this value here gets split between these two, meaning your speed has to be smaller. All right, so I think that's good for this video, guys. We'll pick it up here in the next one.